So we want to prove this if this polynomial has a non-zero term, so some term with non-zero coefficient. Then, and there is some list that we can choose number from this list for each variable. Then by some choice, some evaluation, the polynomial is non-zero. If you take the contrapositive, then it says that this polynomial is zero polynomial. I mean, this is zero whenever, at the variables are chosen from the list. Then all coefficients are zero. So this is something, contrapositive. So this is what we want to prove. So consider the following lemma. So let f be a polynomial in n variables, say x1, x2 to xn, over a field, say f. And for each I, we let the degree of f as a polynomial in xi be at most ti. And let si be a set of ti plus 1 distinct values in this f. And if we know that this polynomial is zero for all values x1 to xn in this si, so x1 is chosen from s1 and xn is chosen from sn, then f is identically zero. So this is what we want to prove. And let's consider the simple case. When n is 1, what does it say? So when n is 1, that means this is one variable polynomial, and one variable polynomial of degree at most t1, which vanishes on t1 plus 1 value, more than t1 value. Then it's known that the graph must be vanishing everywhere. So this is identically zero. So this is zero polynomial. So this is known. So this is a base case, and then we use induction. So we already know this is true for n equal 1. So assume n is bigger than 1. So we collect the terms to write this f as a polynomial in one variable, the last variable, xn. That means, let's say f is a summation of, say, j from 1 to t sub n. It's, you write all the terms and you write all the parts which relate to x1 to xn minus 1 in here. You write xn to the j at the last, where each fj is a polynomial having degree at most ti in each in xi for each I between n1 and n-1, between 1 and n-1. So if you write it this way, we know that this has a degree in first variable at most t1 and degree in second and third and so on. Then let's fix the all first n-1 numbers. We choose s1 to sn-1 some number, and then we evaluate this f0 to ft sub mn at here this gives a one variable polynomial in xn, because you already plug in all n-1 numbers, so they all becomes number. So now this becomes a polynomial in one variable. The remaining variable is xn, and which has degree at most tn. Moreover, the hypothesis implies that this polynomial has value 0 when evaluated for any Sn in this capital Sn. So we have plugged in all n-1 number, and then last number we haven't put it yet. So we have this one variable polynomial, and now we put this number. But there are how many choices? dn plus 1 choices. So let's write it this way. For each this choice out of tn plus 1 choices. Then what do we know? By the base case, when n equal 1, the one variable polynomial vanishes at more than dn points, and having degree at most dn must be identically 0. So once you plug in this n-1 in some way, then the resulting polynomial, one variable polynomial, is the zero polynomial. Thus, what does it mean? Then each fi is 0 at all values in here. Then this is exactly the induction hypothesis. We assume that we use induction, so we assume that the statement holds for n-1. So by the induction hypothesis, each fi is identically 0. Thus, the coefficient of f are all 0 and f itself is identically 0. So this finishes the lemma. So this is almost what we want, but there is some points that some points that's not so good for us. So we take this SI with a set of DI plus 1 distinct values in here. So what we want to conclude is so this is what we want because of our setup. If we have a xi, say ti has non-zero coefficient, let's say okay x1 2 x2 1 x3 3. Let's say this has non-zero coefficient. Then this number 2, 1, 3 are the out degree. So what we want to do is when we have S1, S2, S3 of the list of the colors that we use, and if it has one more than this number, say this has 3 numbers, and this has 2 numbers, and this has 4 numbers, then we can choose one from each so that the entire polynomial does not vanish. That's what we want to do. Because we show that we assume that this is non-zero, that means this is non-zero. And this value, each of these values, is plus 1 is our FBI. This out degree plus 1. So that's what we want to do. But what if we have terms, there are more terms. Like this. Let's say this is our polynomial. We know that this has non-zero coefficient, but there are other monomials with a non-zero coefficient. In that case, if we directly apply this, if we want to apply this, then this di is the degree of f. So for x1, so in this case, d1 must be 3, d2 must be 3, d3 must be 3. So in our conclusion, we want to use this 2, 1, 3 to conclude that we can choose from the 3 to 4 side. But if we directly apply this, then now we have to make sure that every vertex has at least 4 available colors, which is weaker than what we want. That's because we assume that di is the degree of the entire polynomial. So here you see that the older terms has degree 6, but this sum is much bigger. So in order to prove, what we want, we need slightly stronger statement. So this is something called combinatorial null-Stellangers. The name comes from the Hilbert null-Stellanger. But anyway, so this is exactly saying what we want. If we have this monomial with non-zero coefficient. In a polynomial f which have degree summation of this ti over a field f. So this is the situation. It has degree 6, total degree 6. And then this number sums up to 6. And S1 to Sn are sets with Si, each Si has size bigger than Ti for each I. Then we want to show that this fx is non-zero for some, say, vector s, x, x1 to xn. Here. So this is what we want to prove. This is called combinatorial Nullstellensatz. So, on the lecture 16, I went over time quite a lot, so let's make the lecture 17 a bit short. So we will stop here, and then next time we will prove this, and then we will finish the proof of Allon-Tarski theorem. And then we move on to some other application of this combinatorial Nullstellensatz, which may not be related to the graph coloring. So that's what we will do next time. Thank you for listening.